Okay, so this is the second half of 6.5, and it's all about the logistic differential equation. Anybody know what you call the one that we already developed? The one that was started out dy dx equals ky?
The
The exponential differential equation. And by the way, as you get further and further in math, they won't call them differential equations. They'll call them diffie-qs.
Diffie-qs?
Diffie-qs. Every time I say differential equation, first thing I think of is a diffie-q, but I haven't told the kids that, so I better call it a differential equation. So the first one that we did and found the solution to it, y equals y naught e to the negative kt, or kt, whichever one. That solution is the solution to the exponential diffie-q. Just to remind you where we're headed, I just need to show you something that was based on this idea that the derivative of y with respect to x was equal to some constant times the amount of stuff we have right now. And this is constantly changing. And we solved this by separating variables and integrating both sides and taking care of the c, and we ended up with this. Do you remember?
Yeah.
This k right here ended up being this k. And it was actually a t up here. This would have been dy dt if that was the case. So then we end up with y equals something with a t in it. And this is the solution to the exponential idea diffie-q. The rate at which something's changing is proportional to the amount you have now. And this is its solution. Today, we're going to find the solution to the logistic diffie-q. And it's quite a bit more involved. Logistic curves are generally used to predict the number of members in a population over a long period of time. And they've got a picture of it on page 365. There to the left. It goes up exponentially for a little while. And then it flattens out. It approaches an asymptote called the carrying capacity. You've studied this before, right? Okay. This is the notion. This is the differential equation that goes with it. The reason they're using P is because it almost exclusively applies to a population. I'm going to start over here because I'm going to need a lot of forward space. The PDT is equal to, it's a little bit more involved. Can you see it? What they're saying there is equal to Kp times m minus p. So this part of it looks an awful lot like the exponential part, the exponential one. It is the exponential one. Then they multiply it times m minus p. And we're going to just try to figure out why that is. Look at the exploration on page 365. We're going to go through this. Jen, get off your phone. Okay, this is our differential equation that we're talking about now. I want you to consider just this equation. We're not going to solve it yet, just this equation, what it is. And it says, consider a positive population that satisfies this differential equation, where k and m are positive constants. Okay, here we go. For what values of p will the growth rate dPdt be close to 0? So think about the right side of that. What values of p, we're talking about population now, for what values of p will the PDT be close to 0?
It's close to the carrying capacity. So we already be at value.
When p is close to the carrying capacity, right? And by the way, carrying capacity is n. Can you see that if p is close to that, then m minus p is a very small number?
Yeah.
When else will it be close to 0?
Wait, k is just, okay, k is a constant.
K is a constant. Won't affect the size of things.
So p times. Why is it p times m minus p?
Right?
The p times the m minus p doesn't make sense. Why would it be p?
Okay. Let's discuss that first if you want to, so that it makes more sense to you. And then I don't think it'll help you answer these questions, but let's discuss that. It says I'm going to go ahead and read this stuff that's right below the big words, the logistic differential equation. Let's see if we can understand where this stuff comes from. It says, now consider the case of a population with a growth curve as a function of time that begins increasing and is concave up as an exponential growth, then turns increasing, still increasing, but concave down and appears to approach a carrying capacity for a habitat. A logistic curve like the one shown has the shape to model this growth. We already discussed that shape. It says we have seen the exponential growth at the beginning can be modeled by this differential equation, dp dt equals kp. If we're talking about just the beginning part, it does look like an exponential growth for a little while, yeah? But then we have to start restricting that growth. It still is increasing. The population is still going up, but it's going up at a much, much slower rate. We've got to have something that will pull that growth rate back down to something flat. And that's where your M minus P comes in.
So.
And M is the carrying capacity. So if P gets closer and closer to M, the growth rate gets closer and closer to zero.
So if we derive that, would we get a logistic function?
You don't derive this. This is
And
the
I derive.
Possibly. Yes, you will. We will.
Because it's,
Because this is the differential equation belonging to logistic growth.
how does that work though? Because don't you have a quotient in the logistic function?
When we solve it, you will see it will be the logistic function. Okay? But conceptually speaking, remember when we started out, we said dp dt equals kp? Or dp or dy dx equals ky? Remember that?
Yeah.
And you all seem to buy into the idea that a constant times however much we have now is how fast it's growing at the moment?
No, that's how much we have at the moment.
What at the moment times a constant is how fast it's growing?
Oh, without this, yes.
Yes, without that. We bought into this idea here with the exponential.
One. Yeah.
Okay, now we got to try to figure out why this is the logistic one. And it all has to do with this guy right here. If M is the carrying capacity, then as the population approaches it, it pulls this growth rate back under control instead of letting it go out of control like an exponential would. This is the bring it back into controller. You see what I'm saying? Does this make any sense to you?
Yeah.
Okay, so there's two times in this curve when the rate at which population is changing is close to zero. It's when the population itself is close to zero. If the P part right here, if this is a small number, then this product will be small, which is what the change is. And if this number is small, multiplied by these, will make this smaller. So there's two times when the rate at which it's growing is small, and that's at the beginning and after it approaches the carrying capacity. Does that make any sense to you? We're talking about a growth rate here, folks. Just so you understand, I'm going to erase this curve, but I need to talk to you for just a minute about what we're talking. This is a growth rate. It goes like this. Growth rate means to us, as calculus students, slope of the curve. Slope of this curve is tiny here. The slope of the curve, as we get up here, is tiny. Still going up, but it's very small. In between here, it gets steeper and steeper and steeper, and then it's about as steep as it's going to get, and then it starts to shallow out again. But right at the beginning and near its approach to the carrying capacity is when the rate at which it's changing is very small. Because this is a rate. And that means to us slope. Okay? Does that make sense? All right.
Okay.
Number 2 says, as a function of P, that is P is like
Why
this,
don't
like
we have a T there? I know, but why isn't there a T in that function?
There will be soon. As a function of population, the population, y equals kp to the m minus p has a graph that is upside down. It was, excuse me. Sorry. Okay, hang on just a minute. This is a new consideration. This is still a rate at which population is growing, but I want to consider this thing as a function itself. Derivatives are functions, right? So consider this as a function, y equals, that's why we're taking the dp dt off. Don't think of it as a rate of change anymore. Just think of this as a function, kp times m minus p. It's just a function we're thinking about. And p is the variable. M is a constant, k is a constant. Okay? P is the variable. So the question asks, if you're considering this as just a function like you did in Algebra 2 and in pre-calc, if we consider that as a function and graph it, it's an upside down parabola. isn't it?
Yeah.
If P is the variable, then you get KPM minus KP squared. And the negative KP squared makes it a parabola opening downward.
Yeah.
Do you agree?
But
Don't but anymore, just stay with me. Consider this function, it's an upside down parabola. Will we all agree with that?
Yeah.
Written in terms of P. P is the Y value. No, P is the X value, sorry, P is the X value. So, what's the value of P at the vertex of the parabola? Let's make this a parabola that looks a little more like what we're used to seeing. This would be negative K P squared plus K M P. This is our variable, right? So if I have that function, I'm just thinking about that. How can I find its vertex?
you put it in standard form.
It is in standard form.
You take it out of standard form. No, it's not.
Yes, it is.
It is.
It's not in vertex form.
Okay, so the vertex is.
What's the x coordinate of the vertex of a parabola?
0.
No, negative b over 2a.
Oh.
Isn't it?
Yeah.
Okay. What is it in this case?
Negative kn over 2 negative 2k
Which is?
m over k. M over 2. Over 2.
That's a cool thing to know. And I'll tell you why in just a minute. But the vertex is m over 2. The vertex of this parabola is m over 2. What else did I want us to find? Oh, just the vertex of the x coordinate of the vertex. Now, use the answer in part 2 to explain why the growth rate is maximized when the population reaches half the carrying capacity. That's mouthful right there. The vertex of this parabola, which was a differential equation, the vertex of this parabola is m over 2.
Meaning that that's when the logistic functions increase the most.
Exactly. Because this is the derivative of the logistic function. We haven't recovered yet, but this is the derivative of it, which happens to be a parabola. So if you're looking at the graph of a parabola that goes like this, and this location right here is m over 2,
And the derivative of that would be 0, which is where it's just concave.
you're right, this has a derivative of 0. It is positive before and negative after, making this for the original equation what? A maximum.
Wait, for the original equation?
This is the graph of a derivative.
Yeah.
Then that means that when this slope is 0 and it's positive before and negative after, that the original function P equals has a maximum there.
Maximum rate.
Maximum rate, yeah.
Oh, okay.
Yeah. Sorry. Maximum rate, exactly.
I was very confused.
So, I know. I said that very wrong. That was really bad. It was very confusing. So if we take the logistic curve for which this is the derivative, listen, this is the derivative of a logistic curve like this. If this is m, which it is, the carrying capacity, where will we find the inflection point?
At this. But wait.
At m.
But is that based off of? Oh no.
Sam.
Okay, would that distance be from this point? Is it halfway between?
No.
here
It
and
is
the
half
X?
of. It's
Okay.
from 0 to m. I understand your question. That's good. It's good. I was going to bring that up, but I'm glad you did.
I didn't know how-
It's not halfway between here and here. It's halfway between 0 and here. M over 2.
Wait, say that again?
The inflection point of the actual logistic curve will be where the derivative of that curve has a maximum.
Okay. Well, like, what were you saying, like halfway between that?
Yeah, he's saying, is this number right here halfway between the initial population and the carrying capacity, or between 0 and the carrying capacity? It's between 0 and the carrying capacity. Whatever this carrying capacity is divided by 2 is the Y value where the inflection point will occur.
Okay. So if your initial capacity was near that half, what would that do? Would that mean it's already started at the
Yep,
inflection?
it's already going to, your population is already starting to decrease its increase.
Oh, I guess because we're T, okay.
If your initial population, by the way, if your initial population is bigger than your carrying capacity, then the environment will also approach that. And they'll start dying off faster than they're being born.
Uh-oh.
Okay, let's see. Next question. If the initial population is less than M, this is the question you were just asking. If the initial population is less, is the initial growth rate positive or negative?
Wait,
If the initial population is less than M,
It's gonna be a negative positive.
then the PDT will be positive because it will be wanting to go up to approach that M. This is what I was just telling you. If the initial population is greater than M, then the initial growth rate will be negative because it's got to come down to approach that carrying capacity. Okay? The growth rate will come down. Okay? If the initial population equals M, what is the initial growth rate?
0.
0, and unless something changes, it'll just stay there. That as many births as you do that. Number 7. What is the limit as t approaches infinity of P of t?
The carrying capacity, M.
M. Does it depend on the initial population?
No.
No matter where you put the initial population on this graph right here, it will approach M, whatever that is, if nothing in the environment changes. Okay, that was our exploration. Gives you a little more insight into this idea right here, this differential equation for logistics. Also gives you some kind of cool information about inflection points. When it stops, when the growth rate stops increasing and the growth rate starts decreasing even though the population is increasing. Do you understand those words?
Mhm.
Okay, all right. All right, now our next goal is going to be, and this is going to take a little bit of time, try to stay with me. Do not write anything down. Use 100% of your concentration to stay with me on this. We are now going to solve this difficulty by separating variables, integrating, all that kind of stuff. Just like we did with the KP one, with the KY. Okay? Here we go. And then we're going to use what we learned from it on example 4. On example 4, they wanted me to use example 4 to develop it. I don't want to. I want to do it in general and then use it on every problem that we have. Okay? Here we go. Here goes. Hang in there. First thing to do on a differential equation that we've learned so far anyway is to separate the variables if possible. Now remember, P is serving the same role as Y usually does. P is the Y-axis, T is the X-axis. Okay, and M are constants.
Oh, okay. Could we just first factor it out? This should be the KP.
Remember, M is a constant.
So just KPM minus P squared.
Yeah, so this is how we're going to separate it. This may not be really obvious, but here's how we're going to separate it. Is that okay? Because this is a constant. These are P values that all fits underneath P. Don't understand that separation? That's the first hard part. There's so many variables and they're not variables. You have to remember constants have to be treated like constants. So this is our first deal here.
Why did you decide to keep the K over?
Because I like to keep this as simple as possible. I like to keep this left side as simple as I can, even though that's not very simple.
I guess.
What do we do next?
And use substitution. No.
Integrate it.
Integrate it. You see
That's where
why
our
we
T
needed to
comes
learn partial fraction decomposition first?
from. Yeah, that's where our T comes from.
Yeah, that's where your T will come from. But do you understand we're going to need partial fraction decomp on this?
Because it's squared.
Yeah, because if you FOILed it out, it would be squared and you can't use a logarithm on it. You can use a logarithm on each of these, but they need to be partially fractionally decomposed.
So that equals.
So this is my next part, is to try to integrate this. I'll come back to this in a minute, but I want to try to integrate this first based on what you learned and practiced yesterday. So this piece right here, without integrating, just the dp, I'm just going to call it 1 over p times m minus p. What is that equal to if I want to decompose it?
A over
Fractional.
P
A over p
plus B over M minus P.
plus b over m minus p. That's how we begin. And then what? Common denominator. Multiply through by it. That's 1 equals a times m minus p plus bp. Now what?
We solve for one of the variables by plugging in something else that will
Make
go to
M
zero.
equal P. Can you do that now? Make P equal M.
Let P equal M, is that right?
Yeah.
Then I have 1 equals,
Zero plus
Yeah.
BM.
Just be.
Yeah.
so what is B?
1 over M. That's weird.
Okay, now what?
Make P equal 0.
Let P equals 0. That gives me 1 equals
AM.
AM. So A is
1 over M.
1 over M. They just happen to be the same thing.
So,
Or M to the negative.
So, do you want to come back and write the integral now, or do you want me to come back and rewrite that and then write the integral?
let's just go back and write the integral.
Are you okay with that? So this integral right here, so well, I guess left side is going to become the integral of A, 1 over M, over P, plus, dP, times or plus the integral of 1 over M over M minus P dP. See what I'm doing? Equals the integral of K dt.
How is this an easy way? Because then you
Can we take the 1 over M outside the?
Yes, and I will, but I'm trying to be true to this for right now. Is everybody clear?
Yes.
So you're right. We can do 1 over M out here because that's just a constant. I'll go ahead and write this step times the integral of 1 over P.
Wait, if M was a variable, then you couldn't do that, right?
Right,
Oh, just
right.
use the constant.
Give me a wrong.
Okay, now let's integrate.
Can we not do anything else on that second one? Why not take another 1 over M now?
You could take the 1 over M outside the whole thing, which we'll do in a minute, but let's integrate these separately with the 1 over M's hanging in there, okay?
1 over M natural log P.
Does P have to be absolute value?
Yes.
No.
No, population will always be positive. It can't even be 0 and get anything growing.
Minus P.
I always want to make an absolute value.
Could that be, that should be an absolute value, shouldn't it?
Yeah, KT right there.
Yeah, but M minus P.
You're right, I'm not going to. We're gonna talk about a growth.
Okay. That's it, right?
Is this right?
Yes.
Oh, is it? Plus no.
What?
Plus
Plus.
C.
Well, part of this, right?
Yep.
Now what?
We, isn't that what we were looking for?
No, we have to solve for P. We've just integrated, that's it. We got a lot of work to do on this. What? If we had an initial condition, we would.
Oh,
We don't.
Multiply by M.
It's just gonna tag along.
Multiply by M.
Multiply by M, okay, I'll do that. Natural log of, so I'm gonna multiply everything by M, that's what I'm doing. Natural log of P plus the natural log of M minus P equals M KT plus MC. You're going, but that's just a C. Yes, but since we didn't actually have an initial condition to find anything, this now becomes subject to anything we do algebraically.
So it's acting like one of those constant variable things.
One of them constant variables, all right?
Can we put
Do you have to-
We have
Yeah, can we
natural
find
log
the
of P
natural
times M minus P. You multiply them.
Or you could just raise it up.
Oh, guess what? There is an initial condition. What is the initial condition?
0.
Initial population.
The initial condition is, and this is gonna drive you nuts, we're gonna introduce another constant variable. The initial condition is this. at time t equals 0, the population's P naught.
Oh my god.
0. That's your initial condition. So I'm going to erase this,
Ouch. No.
and we're going to go find C. So when t is 0, P is P naught. Right?
Oh, so.
So this is, if it's okay with you, I'm going to do some algebra here. 1 over m times the natural log of
Yeah, minus.
p times m minus p. Because it's a sum, it becomes a product, right? I factored out the 1 over m.
Yes.
Okay. But these are p naughts. Well, I won't go that far. I won't go that far yet. I'm just condensing here a little bit. Equals k t plus c. If t is 0, can you see that this is c? If this is p naught?
Oh yeah.
1 over m times the natural log of p naught times m minus p naught equals k times 0, which is c.
Oh.
You see it?
Uh-huh.
Okay.
So now we have to find what C is right now.
That is what
That is what C is.
That is what c is. We have to put c in there.
Okay.
We have to replace this
Ew.
with that.
Yep.
Are there any numbers in this whole thing?
Yeah,
There will be eventually. There's a couple ones in there right now. There will be a couple of 2s here pretty soon, I think.
Okay.
All right, now I have to go over to the next board and I don't want to erase this. So we got to take these people over there.
You hate math.
Unplug me for just a minute. Just unplug it, it's okay. It's got enough battery for that. All right.
The ladder.
Well,
They'll just have to deal with the glare if they want to watch this. Let's see, right there. Okay. Hope you can see this past the glare, everybody. Okay, so now we're continuing on to this board, and it would be awful. I mean, it would be nice if I could point to the other board for you, but I can't. So good luck. So if I rewrite this line right here and replace C with this is what I get. 1 over m times p, no, the natural log of p times m minus p equals kt plus 1 over m times the natural log of p naught times m minus p naught. Is that right?
Yeah.
Yes.
Okay, we've got our initial condition, doesn't involve a c anymore. Now let's multiply by 1 over m. That will at least eliminate fractions. So if we multiply this by m, not 1 over m, I meant m, to eliminate the 1 over m. It's going to be the natural log of p times m minus p
MKT.
equals mkt
Oh, just L and P naught.
plus the natural log of p naught m minus p naught. Okay? Okay so far? Let me see what I've gotten to. Now we're going to do some clever things that may not occur to you to do.
Should we subtract the natural log?
No.
Minus,
Because it's P naught and P.
it doesn't matter, you
But
just do it.
Oh, wait. I
Okay,
can put some.
Yes, you can. You subtract it over on a separate term, so then you divide it, because you can do that with natural logs.
There was something we forgot.
Oh, no.
Earlier?
Okay,
Oh, no. Oh.
can you figure out what it is?
No.
Tell us where we forgot it.
We forgot it when we integrated.
Chain rule.
Ooh, just done.
Were we allowed to do the natural log of m minus p like we did?
Yeah, do we need to
Where
make
did
that?
we? No, it's linear.
Yeah, it is negative.
What is?
This
The
right.
second one.
Yeah, that's right.
Because it had
Because it's a
actual
negative
values on
p,
it.
so we natural log the negative p, so then it's times t, whatever that is, so.
You have to account for the fact that that thing's derivative has a negative in it. So we need a negative in ours. You're right.
It would be negative
Chain.
out there though?
Yep.
Okay.
Chain rule. Because the integral of this is the natural log of m minus p times something to account for the fact that the chain rule in its derivative would have another negative in it. So we need a negative, negative.
So now we're gonna have the natural log of
Yes,
p
yes,
over.
hang on. We've got to fix this now. This isn't the case anymore, is it?
Oh,
So that's not gonna be C.
Nope, it's not gonna be C either. This thing, when we lump these logs together, is going to be P over M minus P.
Guys, why didn't say it's
Oh, no.
See how quickly forgetting that negative causes problems? Listen, shh, shh. So if I put P naught in for P and let T be 0, that's just gonna change this to being a fraction also. That's all it's gonna do.
Oh,
We're saying we're gonna plug P naught in here for P, so that'd be P naught over M minus P naught. And then this is still 0, so C is this now. So when we come over here, we gotta fix things.
okay, not as bad.
Yeah, it's not as bad as that, but still, it changed it from a product to a quotient, which is pretty important.
It's gonna be a mess.
And I totally forgot about it. I knew what to expect, because I've done this before, and I'm going, where's my fraction? Where's my fraction? Oh, crap. So, oh crap, we integrated wrong. We forgot our chain rule, which is extremely important. So I'm gonna start over here. On this part right here. So we're gonna bring that over here and put C in where it goes. So here we go again. 1 over M times, read it to me.
Natural
I'm
log.
talking about the next to the last one, but we're gonna replace it with it.
The natural
Natural
log.
log.
1P over M minus P
Okay,
equals KT. Oh, close it.
close it. Equals KT.
Plus 1 over M natural log over M minus P naught.
Like that. That's where we are. Okay? Putting C in where it goes. Okay. Now I'm going to pull a trick on you, because if we didn't and we went to the end of this based on what we've got here, we would have to backtrack to here to get it right. So I'm just going to tell you. I'm just going to tell you what we're going to do here. It's perfectly legal, but it might not occur to you to do it if you were doing this. Probably would not occur to you until the very end. And even then you might say, that is totally wrong. It might not occur to you how to fix it, so I'm going to fix it right here. Okay? I am going to not only run a, hang on just a minute. Let's go ahead and get rid of our M first, like we did before.
Okay.
And then I'll pull that little trick on you, okay? So if I multiply through by M, I get natural log of P over M minus P equals MKT plus the natural log of P naught over M minus P naught. Because you don't anticipate where this is actually going, where it's going to land, you may have had difficulty just following it to here, because we made a mistake, we didn't fix it. Here's what's going to happen pretty soon, and you're going to be glad we did this. It's really, really much more helpful in a fraction if you can have a monomial and several terms in the numerator, because you can put it under each one separately. It's a lot easier to handle. How can I make that happen?
Put negative.
Put a negative, well, actually, think about this. Think about this with me. If I just, at this point, I ran an M through to get rid of the 1 over M's. If I run a negative through, will that fix my problem? Will that fix it so that I've got P in the denominator of my logs?
I don't understand. How would I get that? Just that negative? What?
Fractions are much easier to deal with and simplify if a monomial is in the denominator with several terms in the numerator, and I've got just the opposite. Will running a negative through fix that?
Yes, because you can flip them over and then.
Oh,
Here.
wait.
You can just flip it, right?
Yes, but it's important to understand why. Watch. If I put a negative, if I just make this negative because I feel like it, take a look at this and look what happens. If I have the opposite of P over M minus P, remember logarithm property says that whatever this is can become an exponent on this.
Got it.
And can you see that that would give me P to the negative 1 over M minus P to the negative 1, and if I flipped them both over, they'd be positive?
Gavin does it. Could you show how, like, if you did the natural log of P minus the natural log of M minus P, and then you write a negative that way?
That would work as well. Did you understand what he just said?
I'm lost.
If you took this right here, what he's saying is, if you used another property of logs and said, okay, the natural log of P, right now, without this negative on it, natural log of P minus the natural log of M minus P is what we've got, right? If you ran a negative through that, you would have the natural log of m minus p minus the natural log of p,
Yeah.
which would give you the natural log of m minus p over p if I just added a negative. Do you understand that?
Yeah.
So that does
I
it
do.
for both sides, huh?
The other way makes more sense than that.
Okay.
Yeah, it does it to both, yeah.
However you understand it. Are you good? You understand what's going on? You understand? If I want p in the denominator, that running a negative through this logarithm stuff will cause that to happen.
Yeah.
Okay, so if you fully understand that, then this is what's gonna happen when I run that negative through. Now try to keep track, because it's a lot of stuff to remember. If I run a negative through right here, what it's gonna give me is the natural log of m minus p over p. I've already used up the negative in doing that switcheroo. Equals negative mkt plus, it's still plus, because what the negative is going to do to me here is flip that over too. The natural log of m minus p naught over p naught. So the negative on the logs flipped the fraction, but the negative on the mkt became a negative mkt. Follow that?
Yeah.
Everybody good?
But how does?
You'll see the advantage in a minute. Remember, people, our objective is to solve for p.
Oh, okay.
That's our objective.
Well, it's
Solve
P
for
or
p.
P naught?
No, p.
Just P.
P naught is just constant. When we are done, we want p to equal something with a k and an m and a p naught and a t in it. That's what we want when we're done.
Well, now there's no numbers in here.
Now, how am I going to get at p when it's stuck behind that natural log? We're going to e it. Really going to be pretty. Okay? So, if we're going to e it, it's going to leave me with m minus p over p over here. I'm going to take e raised to this equals this. I'm just leaving this here. So this will be e raised to the negative mkt plus the natural log of m minus p naught over p naught.
But the natural log of that minus p naught.
Oh, yeah, you
When
can
we-
separate them.
When we rewrite it, because of the property of logs, if I'm adding my exponents, that's same as e to the first one times e to the next one, and that will happen there. You follow?
Yeah.
Okay, so the next move is to say m minus p over p is equal to e to the negative kt,
Wait.
mkt, times e to this, which is m minus p naught over p naught.
That was amazing. Is that it? No.
No.
It's almost.
Oh.
Are we okay so far? Now, we're going to take advantage of the fact that we flipped those over, and I'm going to call this m over p minus 1. Can you see the advantage of doing that?
Yeah.
Okay, now we have p occurring in only one place, which is nice. So I'm going to go ahead and write what we got over here, negative mkt times, actually I'm going to put this in the front, if that's okay. This is going to be m minus p naught over p naught, because it's just a constant, e to the negative mkt
Plus one.
plus 1 takes care of this.
And then you have to multiply. And then
No,
Now we're going to solve for p.
So everything has to be inverse.
Quick question.
Sort, yeah, we could just tip everything over, except you can't do it with that 1 plus 1 over there. What?
Did you do the same thing with m minus p naught over p naught?
And still.
Yes.
Like do minus 1 and then
Yeah,
take out.
And we might do that in just a minute. Probably we will.
Miss J, wouldn't it still be plus one though?
It's plus 1 over, yeah, it's plus 1 on the end there.
But if you inverse it,
no.
it should be plus one.
You can't just tip over each individual term. If you wanted to take this whole thing and flip it over, we'd have to find a common denominator for this first. And instead of doing that, I want you to imagine this. You guys are sharp. I know you can do this. You can handle it. If I were to cross multiply, it would be m times 1 equals p times this. Then to solve for p, it would be m divided by that.
Wait.
So basically it's m over
Yeah,
the
got it.
right side equals p.
So
Besides the p naught.
m times 1, I'll have m over here equals p times this crap, and then I'm going to divide m by that junk, and that will be p. What?
Because just put the whole right side over one.
Yeah,
And since those.
making it a fraction.
Oh, like that.
Yeah.
Yeah, then it would be m times 1 equals p times this junk. So to solve for p, it would be m divided by that junk.
Yeah.
Okay, If you understand that's how it's gonna work, then P is going to be equal to M over 1 plus M minus P naught over P naught e to the negative MKT, which is
Longer.
the logistic equation, if you understand that this is usually replaced with an A.
Oh.
And that is just a constant,
Can
right?
you write that
And
as
that's
like
how we're
one?
supposed to.
So if you want to write it like that, that's fine. If you want to do it like that, it would be P equals M over 1 plus A e to the negative KMT. But now you're going to have to remember that A can be found by taking M minus the original population over that population. So you can find A this way, or you can find A the more conventional way if you want. But that is a logistic. And by the way, this also says e to the negative KT. That constant right there is actually a constant times the carrying capacity.
Wait.
It's a constant of growth.
What's the more conventional way that you were talking about to find
This is?
A?
Well, if you let T equal 0, then this goes to 1. And so you take your initial population, cross multiply it, you'll know your carrying capacity. That's the conventional way of finding A. This is another way. If you know the carrying capacity in the initial population, you find it this way, which is more direct, but whatever.
That was fun.
Wasn't it?
No.
No.
We put this whole thing in a very organized way on a T-shirt. It took both sides. One of my calculus classes wanted, that was the T-shirt they wanted to do. But we were still taking tests at BYUI at the time for competition, and I had to call them up there and say, we've got our differential equation solution on the shirt. Is that going to be a problem if we wear it to competition? They said, nah, we don't have anything to do with that. So they didn't have any problems doing it. Okay. All right, well, we're going to come back over here and put you back up on the ladder, and then we're going to do some problems over on that other board.
Why don't we do that? We just put everything we need on our shirt. And then come-
Well, what it was, do you remember, what's his name, Barnhill? Gabe Barnhill, not Gabe, his older brother. Remember him?
Yeah, I don't know her brother.
Yeah, he did it.
I don't know. I don't know.
He was in here, and his famous is most, and he did it every single time. When he would come up to my desk, he'd say, so, and then he would present the problem that he and I were going to work on. And it was so funny because we put that at the beginning of the shirt. So, ... And we put the whole thing, because he was also very famous for saying, I'm not going to be able to do this. He was also really famous for saying, wait, what? Wait, what? And so we got the whole thing done at the bottom of the shirt. We put, wait, what?
Hey, stop.
Anyway, the whole thing's on there. I'll wear it for you one of these days, and you can see it. You actually understand kind of what's going on. All right. By the way, I have on here that A is equal to M over P naught minus 1 because of that trick. So if you want to memorize it a little bit, it is exactly what he said, which is that you can do the same trick here that we did with the other one, which is M over P naught minus 1. That's another way of memorizing it. Okay? All right. Now, let's see if we can do a problem involving this.
Will we have to memorize that name?
This whole message, this whole thing?
Just that,
No. You'll have to
yeah.
memorize this, and then it leads to that.
Yeah, you're not getting lucky as Jack Duval after this question. No, I'm never doing that.
So Miss J, what if as a population goes through time, its carrying capacity increases?
Well, then you've got other things going on in the environment, and now you've got,
Your M is no longer just a constant.
right, and if that's a variable, then you've got multiple integrals that are going to,
So you can just plug it in there. Though,
partial
right?
integrals to deal with.
What is the carrying
They do stuff like that, but not until your next section of calculus.
next section? Like,
There's three semesters of calculus. You're only taking the first.
Dude, Baby Shark has more views than there are people in it. Really?
Okay, I want you, before we move on, listen, I want you, before we move on, to look at page 367. 367 at the bottom in the tan box. Do you all see it? Okay, so it gives you the differential equation, and then it gives you a solution, which we just came up with. And one thing it doesn't have on here, although you're somebody in your, whoever had your book last night have written it, which is what A is.
Yes.
And over P naught minus 1. That may be in that box.
That person's dumb.
People, you want to commit all three of those things to memory.
Oh.
The diffie-q, its solution, and what A is. It's going to be very, very useful to you. Now, let's see if we can apply this to a problem. Here's the deal. I'm on example 4, bottom of page 365, so go back. Bottom of page 365 says, the growth rate of a population P of bears in a newly established wildlife reserve is modeled by the diffie-q 0.008 P times 100 minus P, where T is measured in years. We are to ask do these three things. What's the carrying capacity for the bears in the wildlife reserve? You can answer that right now. 100.
100.
Do y'all see how to recognize that out of the diffie-q?
Yeah.
We're at the very bottom of page 365 looking at problem part A.
Okay.
And we have this differential equation, 0.008 P. So we have this, dP, the rate at which the population is changing with respect to time is given by this equation, 0.008 P times 100 minus P. And if you remember what the diffie-q looks like and what these things represent, you'll see that that's M and that's the carrying capacity. We can answer part A if we know where to look right now. B part. What is the bear population when the population is growing the fastest? We can answer that too, and rather quickly. What is it? 50.
Wait, what is the population? Oh, okay.
What is the bear population when it is growing the fastest?
Halfway.
That's at the inflection point. Right.
Oh,
Which is
over
it?
2.
2. When it's growing the fastest is when the tangent line is steepest, and that's at the inflection point of this. Well, it's provided by that. M over 2. You with me or not?
Yeah.
Okay. C. What is the rate of change in the population when it is growing the fastest?
20.
Wait a minute. What is the rate of change when the population when it's growing the fastest? The rate of change when it's growing the fastest is what?
20.
Would you?
We want to find this.
50 by 50 for P. Yeah.
Plug in 50 for P, and you said it's 20? 20 bears per year when it's growing the
I don't
fastest?
trust you, Sam.
That means of your 50 bears, at least 20 of them have got to be female. Probably a lot more because generally there's only one dominant male, but one or two
Should do this to me.
and a habitat. Okay?
Oh, dang.
So that was using just the differential equation, not even the solution. We were able to answer those three questions. Is that right?
Yeah.
Now turn the page and let's do example 5. Let's see if we can answer these kinds of questions. Here's what it says. In 1985 and 1987, the Michigan Department of Natural Resources airlifted 60 lawn moves. Not all at once, people. Not all at once. Probably one at a time. One under each helicopter. And they may have used 4 or 5 helicopters at a time, but they only lifted a few at a time.
Just big old bag.
Yeah. Try lifting that. That's what. Anyway, what they're doing is transplanting moose into a habitat. Okay? From Algonquin Park, Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach a carrying capacity in about 25 years with a growth rate of, so they're giving you the diffie-q again. Now let's see if we can answer these questions. According to the model, what's the carrying capacity?
10,000.
Okay. With a calculator, generate a slope field. We can't do that because we never studied slope fields, so forget that. C part. Solve the differential equation. Thank goodness we already did. With an initial population of 61 and show that it conforms to the slope field. We didn't do the slope field. What I want to do is try to figure out what the solution is based on the differential equation. That's what I want to be able to do without going through the whole process and covering the board again.
What solution?
The solution to this differential equation.
Oh, okay.
What is this right here? Tell me again what the
0.0003 P times 1,000 minus P. 1,000.
Now let's see if we can fill in the details to the solution that we know is this equation. P is equal to what? M, which is 1,000, divided by 1
plus
plus
This is
1,000
over 61.
over 61 minus 1.
Wait, why is it 61? Oh, God.
Is this the initial population?
Could we just leave it as 1,000 over 61?
Okay.
That's nasty.
1,000 over 61 minus 1?
Oh, yeah.
We'll take out
Oh,
the
you just get rid of the one then. No, because that's not
So
D.
That's 1 plus.
So,
And then it's A. A is what we're trying to come up with.
so parentheses. Oh, wait. Should I just do this?
It's gonna be 1,000 minus 61 over 61. What's 1,000 minus 61?
You mean 1,000 over 61?
No, I'm doing the fractional arithmetic. This is 1,000 over 61 minus 61 over 61. That's why I'm saying, what's 1,000 minus 61?
So we get 15.39.
I don't want that. I want to know what 1,000 minus 61 is.
939.
939 over 61. That's our fraction. That's what that fraction works out to be. You understand what I'm saying?
Yes.
E to the negative, is it negative?
Yeah.
Okay, negative, and what is K?
It would be the 0.003 times our carrying capacity.
1,000
Okay.
times
25, which is 0.3.
This is 0.3?
Yeah.
The negative Km is 0.3?
Yeah, just negative 0.3.
Oh,
Negative 0.3.
yeah.
Did y'all figure how we figured that out? Took M times K. This is M, this is K. This is M, this is K. Okay? So that's what we've got, and we can predict the population at any moment T, and it should have settled on about 1,000 after 25 years if they were correct about their ideas. I don't know. Moose quite often have twins, and if they
How
have,
did we get negative
sure they're
0.3?
survivors,
Oh,
it's
1,000
gonna
times
go. Anyway, we'll do more of this when we get back here on Monday, but you have plenty to work with to get your
So
homework going.
what we're basically solving is they're hoping it's within 25 years, but this will show how long it actually takes.
Well, if you put 25 in for T, you ought to get pretty close to 1,000.
Yeah,
Yeah, see you, bye.
What?
What? You put in